Up till now we discussed the wave propagation in an unbound or semi bound media. We investigated specifically the refraction and reflection of electromagnetic wave across the dielectric boundaries, and lastly we also saw the reflection of an electromagnetic wave from a conducting boundary. Now we take up a very important topic of electromagnetic waves, and that is waveguides. As the name suggests, waveguide is a structure which can guide electromagnetic energy along it. We have a variety of waveguides in practice. For example, the coaxial cable which we have seen as a transmission line also is a wave guiding structure, because it can guide electromagnetic energy from one point to another. The parallel wire transmission line is also a wave guiding structure. However, as we go to the higher frequencies, these waveguides have excessive loss, and that is where you get the waveguides which are like hollow pipes, which are more efficient for transmitting energy at high frequencies. So, when you go to the frequencies like gigahertz or tens of gigahertz, that time the coaxial cable or the parallel wire transmission line, though they are wave guiding structures, become more lossy, and then we get the waveguides like rectangular waveguides, which is like a hollow pipe whose cross section is rectangular, or a circular pipe whose cross section is circular. They can transmit energy from one point to another more efficiently. So, in fact, in communication the wave guiding structure plays a very important role. A communication engineer is always in search of good wave guiding structures, so that he can transfer energy at high frequencies very efficiently from one point to another. So, ideally this wave guiding structure should have as minimal loss as possible, so that while transmitting the energy from one point to another there is no loss of power. Also, this structure should have certain characteristics, like they should be small in size, they should be compact, they should be moldable in the shapes and sizes which we want. So, you can carry the energy very easily from one point to another. Of course, whenever we have a structure like this, we always start with the basics, that is the Maxwell's equations, and solve the Maxwell's equation for given boundary conditions, and then we get a solution for the particular problem. However, without going into that approach, which is a routine kind of approach, what we will try to do first, we will try to understand, if we still confine ourselves to the uniform plane wave propagation and try to capture this uniform plane wave between the boundaries, can we get a structure like a wave guiding structure? And that is what precisely we are going to do here, that with the understanding which we have developed from the reflection of a plane wave from a conducting boundary, we will try to develop an understanding for a waveguide what is called the parallel plane waveguide. As the name suggests, this waveguide essentially consists of two parallel planes which are of infinite extent, and the electromagnetic energy is trapped between these two planes. So, the energy essentially propagates along these planes trapped between two planes. So, we now in this lecture we essentially discuss what is called the parallel plane waveguide. As we have seen in the previous lecture, we had taken a conducting boundary and on which the uniform plane wave was incident at some angle theta, and there is a reflected wave, and then by satisfying the boundary condition we saw the reflection coefficient for the electric field is -1. So, this boundary was behaving more like a short circuit boundary, and then the fields which we have in this media is superposition of the incident field and the reflected field. So, by superposition of these two fields, essentially we obtain the electric field in the medium above the conducting surface, and that essentially was given by this. So, we saw that it consists of two types of fields. One is the standing wave kind of field which is in x direction, and there is a travelling wave field which is in z direction. So, we had seen there is a pattern whose amplitude varies, the electric field amplitude varies as a sinusoidal function in the x direction, that is perpendicular to the boundary, and along the boundary you are having a travelling wave which is having a phase constant which is beta times sin theta. So, this boundary, as this demonstrates, has a capability of guiding a wave along the z direction, because we are having a net travelling wave which is travelling along z direction. Precisely that is the phenomena essentially we are going to make use of to get a more guiding structure. That means I will trap the energy from both sides now. At the moment the energy is not trapped, energy is travelling into this semi infinite media. We will try to trap the energy even from this side, so that energy propagates in the two planes, something like this, which we call as the parallel plane waveguide. And then we said that the electric field which is tangential to the interface, in this case, has to be 0 at the interface. That means that x equal to 0, the total electric field should be 0, and that is what we got this condition from. So, when beta x cos theta is 0, that means when x is equal to 0, that time the electric field goes to 0, so it satisfies that boundary condition. However, what we also saw that not only at x equal to 0, but there are some other values of x also for which the tangential component of electric field will go to 0. So, whenever we have beta x cos theta is multiples of pi, where m is an integer. So, when beta x cos theta is equal to m pi, or x is equal to m pi divided by beta cos theta, for those values of x, again the electric field would be 0 everywhere. And since the electric field is oriented like this, perpendicular to the plane of the paper, which is the y direction, if we put a conducting sheet here which is tangential to this electric field, which is 0 at this point, it will not affect the boundary conditions, because the electric field is 0 here, and boundary conditions demand that this tangential component should be 0 at the conducting boundary. That means at this value of x, if I insert a conducting sheet of infinite extent like this, the fields will remain unaffected. What that then means is that not only the value x equal to 0 where the condition will be satisfied, but I will have some other value of x, another value of x, another value of x, at which if I insert a conducting boundary like this, these fields whatever we have got will remain unchanged. I will get the same field distribution. So, by substituting the value for beta, which is 2 pi by lambda, where lambda is the wavelength in medium 1, I can get this x which is m lambda divided by 2 times cos theta. So, for m equal to 0 or 1 or 2 or 3, I get different values of x at which this boundary can be inserted without affecting the electric or magnetic field distribution. So, these boundary locations essentially, as we saw the plot of the magnitude of electric field, it would go 0 here, it would go 0 here, it would go 0 here, here. So, I can insert a boundary at this location, this location, this location, and the field distribution will remain same. However, by inserting a boundary at this distance, essentially now the wave is trapped between these two boundaries. So, I have created a structure which is more closed structure, it is no more a semi infinite medium. Now, it has become a bound medium in the x direction. So, this was one interface, this is another interface, and now the field is trapped between these two boundaries. Similarly, I can put the plane here, so I can get a boundary like this, or I can get here, and now the energy, electromagnetic energy is trapped between these two parallel planes. Precisely that is the structure we are trying to investigate, and the separation between these planes essentially is given by this condition. So, let me redraw the structure. This is the original boundary which we had, below which we have a conducting medium. This is the x direction, this is the z direction, the y direction is perpendicular to the plane of the paper, and let us say the wave is incident at an angle which is theta. So, the reflected wave also will be at angle theta, and we had considered a case here where the polarization is perpendicular, that means the electric field was this. So, this is EI, and then we had got here ER, which was equal to minus EI, because the reflection coefficient was -1. So, that means this reflected electric field has same magnitude as the incident field, only thing is it is negative, that means its direction is reverse. So, if this field was coming upwards, this field essentially should be going downwards. And then the magnetic fields for this, where this was HI and this is HR. And for this, then we had write down the components of the electric field and magnetic field. So, we had 3 components for this case: the electric field, which was y oriented, and the magnetic field, which will be either z oriented or x oriented. So, magnetic field now lies in the plane which is xz plane, it has 2 components, and the electric field is y oriented, which is perpendicular to the plane of incidence. That is the situation essentially we are considering. And now we have got this condition here that x is equal to m lambda upon 2 cos theta. At that location, again the tangential field will go to 0. So, we will have one location here where field will go to 0. I may have one location here, or I may get next location where there, which will be double of this, and so on. So, this distance is lambda upon 2 cos theta from here to here, where this field will again go to 0, or if I go to double of that, it will be lambda upon cos theta. So, this distance again lambda upon 2 cos theta, this distance. So, this electric field which is tangential to this interface is 0 here, it is 0 here, it is 0 here, and so on. So, in fact, I have multiple location of planes where this component, tangential component of electric field, will go to 0. So, what we are saying now is that if I introduce a plane at this location, then the field distribution will remain unaffected. However, only thing which is going to happen is that when these planes were not there, the fields are distributed everywhere in this semi infinite space. However, when I introduce now a boundary at this location, the fields are only confined to this region. We do not know what is going to be in this. So, essentially we will have propagation of electromagnetic wave only in this region. Or in other words, one can say that the wave which was coming here at an angle theta, it goes, and when it goes here, it reaches this boundary, again it will be making an angle which is theta with the normal. So, wave gets reflected from here at the same angle. So, it will appear as if the wave is moving, coming here, getting reflected, again getting reflected. When it reaches here, again it sees the boundary, get reflected. So, the field which are going to survive in this structure can be visualized as multiple reflections of uniform plane wave. So, wave simply bouncing back and forth between these 2 planes which are conducting boundaries. So, I have a conducting boundary here now. So, between these 2 boundaries, by multiple reflections, the wave by this zigzag path is going to travel along this structure or along these planes which are conducting planes. And the height or the separation of these planes is given by this. What now one can do is one can invert the problem, and one can say, well, here knowing the angle theta, we could find out what should be location of these planes, what should be separation between these planes, so that this field remain unaffected. If I invert this relation, say, well, separation between the plates is given, and let us say that is equal to d. Then what are the angles at which, if the wave is launched, the propagation will be sustained? That means it will satisfy the boundary condition, and the wave will propagate by these multiple reflections around the boundary. So, if I say that I have two conducting boundaries now, and let us say separation between them is given by d, then this d should be equal to m lambda divided by 2 times cos theta. Or if I invert this expression, I will essentially get cos of theta, that is equal to m lambda by 2d. Now, this is very interesting because m is a discrete number, it is 1, 2, 3, 4, so it is integers. So, this quantity is discrete. What that means is that for given value of d, that means for given separation between these conducting boundaries, this angle theta is no more continuous. Wave launched at any arbitrary angle will not sustain in the structure. Only if it is launched at particular angles which are discrete, because m is discrete, then only you can have a sustained propagation of electromagnetic wave in this structure. Now, this is a very significant departure from our original understanding of wave propagation. Up till now, when we talked about unbound media, there was no restrictions on the launching angles, we could launch ray in any direction. When we had a semi-infinite medium, even then we could have any angle of incidence and we had some field distributions in the one medium or both the media, depending upon what this media were. However, now what we are saying is, if we make this structure bound in this direction, then I cannot launch an electromagnetic wave at an arbitrary angle of incidence. If I do that, this structure is going to reject that wave, it is not going to accept that wave. If the wave is launched at these angles which satisfy this condition, which are discrete now, then and then only you can have a sustained propagation of electromagnetic wave. This behavior of the bound structure is captured by what is called the modal propagation. So, what we are saying is, there is the wave which can be launched at discrete angles, superposition of these incident and reflected waves, they are going to create certain electric and magnetic field patterns in this, and you will have a unique pattern created for electric and magnetic field for a given value of m. So, if m equal to 0, I will get one pattern, if m is equal to 1, I will get another pattern, if m equal to 2, I will get another pattern, and so on. So, we have these discrete electric and magnetic field patterns which can survive inside this bound structure. That is what is called the modal propagation of electromagnetic wave. So, we have migrated now from the continuum domain of theta to discrete domain, and that is the significant departure which we have done in the wave propagation. And then these discrete angles are going to create discrete electric and magnetic field patterns which we call as the modal patterns, and this propagation in this bound media is called the modal propagation. There are a few things which we can observe at this point. One is, since for physical angle theta, the cos theta has to be between 0 and 1, for a given value of d, I have only limited number of m's. For example, I can put m equal to 1, I can put m equal to 0, I can put m equal to 1, 2, 3, and whenever this quantity becomes greater than 1, that does not represent a physical angle theta. That means not only that the waves can be launched inside the structure at discrete angles, but we also note that these discrete angles are finite in number. That means for a given spacing between the boundaries, only a finite number of uniform plane waves can be launched at discrete angles which are given by this. But in other words, this is going to create discrete finite number of electric and magnetic field patterns inside the bound structure, which is what is called a parallel plane waveguide. So, this model propagation essentially is the core of all waveguiding structure, whether you take a parallel plane waveguide or you take a rectangular waveguide or you take optical fibers or dielectric waveguides. Whenever we have a bound medium like this, the electromagnetic energy is going to travel in definite patterns, and that is what is called a modal pattern, and that propagation is modal propagation. So, modal propagation is a very important aspect of electromagnetic wave propagation in a bound structure, which is called a waveguide. Once you understand this, then of course finding out the electric and magnetic fields, that analysis becomes straightforward. So, let me write down the conclusion which we got from here, that 1, waves survive at discrete angles in a parallel plane waveguide, and there are finite number of angles at which the wave survives. Now, in the original discussion, we say this is the incident wave and this was the reflected wave. However, when we are having a structure like this, which is a parallel plane structure, this wave which is reflected from here goes and meets this boundary at this point. So, as far as this boundary is concerned, this becomes an incident wave and this will become a reflected wave. As far as this boundary is concerned, this is incident wave and this is a reflected wave. So, there is, once you are having two boundaries, there is nothing like an incident wave and reflected wave. Depending upon which boundary you are considering, the wave can be called as an incident wave or a reflected wave. What that essentially means is, there is nothing like what you should call incident or reflected. There are two sets of waves which are moving. One set of wave which is moving like this, which is having the wave vector which are parallel, which are in this direction. Other set of waves which are moving like that, and superposition of interference of these two waves, plane waves, one moving this way and one moving this way, create the field distribution inside this bound structure. That is what is called the modal pattern. So, what we have essentially is, these are the two boundaries, which are conducting boundaries, and there is two sets of waves, one moving this way, other set of wave which moves this way, and superposition of the fields of these two waves create the patterns which are the modal patterns. So, essentially the propagation of electromagnetic waves inside this bound structure can be visualized as superposition of the two waves which are traveling like this at the same angle with respect to this direction, which is parallel to the boundary or perpendicular to the boundary. Once we get this, then we can get now the field expressions very easily for this pattern. However, before we get into that, let us make one more observation about these fields, and that is, if I look at now this propagation where the multiple reflections are taking place and the net propagation of energy is in this direction, which is along the z direction, the electric field is now perpendicular to this plane of incidence, what we call, which is the plane of this paper. So, when the reflection takes place, the electric field vector comes like this, it gets reflected, goes like that, it gets like that, and so on. So effectively we are having a wave propagation now which is in z direction, and the electric field is like that everywhere inside this medium, whereas the magnetic field is like this and this. So it is, the direction is like that. When it comes here, the direction gets changed, it becomes like this, and the direction gets changed, it will become like this. So the magnetic field, if I look inside the space of between these plane waveguides, has two components. One is perpendicular to this, that means in the x direction, one is in z direction, and since the net propagation is taking place in z direction, the magnetic field essentially has components in the direction of net propagation and in the direction perpendicular to it. Whereas if I look at electric field, the electric field is always perpendicular to direction of the propagation. No matter where I go, I will always find this electric field is perpendicular to the net direction of propagation. That means electric field is having a special nature in this particular case. It always remains transverse to the direction of the net wave propagation. That is the reason we designate this propagation as the transverse electric propagation. So we call this mode, whatever the patterns which are going to set up inside the structure, since these patterns will have electric field which will be transverse to the direction of net wave propagation, we call this mode as the transverse electric mode. So we have now a propagation, what is called the transverse electric mode. That means the electric field always remains transverse to the direction of net wave propagation inside the structure, and in short it is denoted as TE. So those modes for which electric field is transverse to the direction of net wave propagation, we call that as the TE mode. Now if I look at this structure again, this thing here, we can get either a value of, let us say, m equal to 1, that gives me the spacing which will be lambda upon 2 cos theta. If I can take m equal to 2, I can get this spacing for a given launching angle. That means either I can have a set of fields which will be in this, or I can have a set of field which will be in this, and for this region m will be equal to 1. If I go here, m will be equal to 2, and so on. That means though the fields are having the same nature, that means electric field is transverse, I can have different possibilities. Either I can have a region corresponding to m equal to 1, or I can have a case which is m equal to 2 or m equal to 3, and so on, whatever is the maximum value permitted. That means the field distribution which we are going to get in this is characterized by this integer number m. So that is the reason when we talk about the transverse electric mode, we put an index to this mode which is this value m as a suffix, and we say that this transverse electric mode corresponds to this value of m, which could be 1, 2, 3, 4, and so on. So we say that for a parallel plane waveguide, this mode will be TEM mode, where we will see a little more the physical meaning what m represents, but at this point it appears that this m is going to tell at what angle this wave is launched for a particular value of m, so that we have a sustained propagation of the electromagnetic wave. Once we get this, then we can go back to our fields which we have derived in the last lecture, that now the electric field is essentially given by this, and cos theta now is equal to this quantity m lambda upon 2d. So, from here I can get first of all this quantity beta x cos of theta, which is coming in the field expression for the electric and as well as in the magnetic field. So, I can substitute for now cos theta, which is m lambda upon 2d. So, I can write here beta x into m lambda upon 2d. Now, beta we know is the phase constant in medium 1, and now there is no medium 1 as such, it is the medium which is filling this waveguide. That means the medium which is filling the space between these two conducting planes. So, that phase constant is 2 pi by lambda x to m lambda divided by 2d. So, lambda will cancel, 2 will cancel. So, this quantity will essentially become m pi by d into x. So, I have got this beta x cos theta, which is m pi by d into x. So, these field expressions I can replace this quantity by m pi x by d. What about this quantity now? Since the cos theta is given by this, I can get sin theta because I require sin theta here. So, from that beta sin theta, that will be beta square root of 1 minus cos square theta, and cos theta is m lambda by 2d. So, I can write here this is 2 pi by lambda square root of 1 minus m lambda by 2d square. So, I have got now the phase constant which is in z direction, which is this. That is what we get from this field expression, that is the phase constant beta times sin theta, and beta x cos theta can be replaced by this quantity. Once I get that, then I can go to my electric and magnetic field which we derived last time and substitute these values for theta, and we can get the fields for the transverse electric case, and that will be now the electric field E, that will be 2j E I sine of m pi x by d e to the power minus j z beta square root of 1 minus m lambda by 2d square. Similarly, I can write down the expression for the magnetic field which we had got last time. So, we get this is the y oriented. So, this field is essentially oriented in y direction, and I can get the magnetic field which will be having component Hx, which is minus 2 j E I upon eta sine of theta, which you get from here, this quantity. So, sine of theta will be square root of 1 minus m lambda upon 2d whole square. I can write that. So, let me just keep it for time being sine theta, sine of this quantity which is same as this. So, sine of m pi x by d, and this quantity is same, e to the power minus j z beta square root 1 minus m lambda by 2d whole square. And then I have the magnetic field z component, which will be h of z will be minus 2 ei upon eta cos theta, which will be m lambda upon 2d. So, this is m lambda upon 2d cos of this quantity, cos of m pi x by d, and this term is same, e to the power minus j z beta square root 1 minus m lambda by 2d whole square. So, in this configuration now we get the 3 field components which are given by that. So, this is the y component, and the magnetic field has 2 components, one is x and other one is z. So, the fields which can survive in a parallel plane waveguide for an electric field vector which is perpendicular to the plane of incidence will have these 3 field components. Now, as we saw that this quantity here we have, this is now showing you the amplitude variation in x direction, whereas this is the one which is showing you the travelling nature of the wave which is in z direction. So, we have a phase constant in the z direction in which the net wave is propagating, that is nothing but this quantity, which is beta into square root of 1 minus m lambda upon 2d whole square. So, when the net wave propagation takes place now, this quantity beta does not have any meaning, because beta is the phase constant of a uniform plane wave which is bouncing back and forth between these 2 conducting planes. What phase constant essentially we are going to see for the net propagation, that will be this quantity, the total quantity. So, we say now that the phase constant for this mode, which is superposition of 2 uniform plane wave, has a phase constant which is this quantity. So, we say that the mode is going to propagate with a phase constant which is this quantity. So, we say now for the phase constant for the mode, and normally it is represented as beta z. So, let us call beta z, or let me just put it as some beta bar, where beta bar gives me the propagation constant of the modal fields along the boundaries, and this quantity is nothing but beta into square root of this quantity 1 minus m lambda upon 2d whole square. And this quantity, as we know, is essentially sine of theta. So, we have beta bar upon beta, that is nothing but a sine of theta. That is what the expression would be. Now, first thing one should immediately note from this expression is that if I put m equal to 0 in this expression, then the electric field will go to 0, because this quantity will make 0 for any value of x, this quantity will go to 0, this quantity will go to 0. So, the E y will go to 0, Hx will go to 0, Hz will not go to 0 because of this term, but then when m equal to 0, this quantity is 0. So, this field will go to 0. So, what that means is that for these fields to survive inside the structure, I must have value of m which is integer but non-zero, because for m equal to 0 all these fields will identically go to 0. That means these fields cannot survive inside the structure. What does m equal to 0 mean? If I go from here, if I put m equal to 0 in this expression, that corresponds to this angle theta of pi by 2. That means if I put a wave which is parallel to the boundaries, if the wave goes parallel to the boundaries, this wave cannot propagate inside the structure. So if I have electric field like this and if the wave goes like this, so if I have a situation that is, these are the two parallel plane boundaries, and if I try to launch a wave inside this which is having an electric field which is perpendicular to this. Okay. So I am trying to put the wave inside the structure, electric field is like this and m is equal to 0. So this is my EI. If m is equal to 0, this wave cannot survive inside the structure, it cannot propagate, this field cannot get excited inside the structure. Why that happens, we can see a little more physically why that happens, and that happens because what is this quantity m essentially telling you? The m is telling you that if I take m equal to 1, then as x varies from 0 to d, which is the spacing between the two planes, I get 1/2 cycle variation of this field. So what the m is telling you is, inside a structure, if I look at the field distribution, amplitude variation of the field, the m equal to 1 would correspond to a half cycle. So this is x equal to 0, this is x equal to d. So from here, when x is equal to d by 2, this quantity will be pi by 2 when m equal to 1. So I will get the field maximum at this location which is d by 2. So I will get an amplitude variation for this field which will be like that for m equal to 1. If I take m equal to 2, then it will represent one full cycle variation as x varies from 0 to d. So if I take m equal to 1, it will be, so at x equal to d by 2 here, when m equal to 2, this quantity will be pi. So again sin pi will be 0, which will be this. So this will represent m equal to 2. Similarly, as I go to higher values of m, I can get more and more cycles in that. So it will be like this. So this will represent m equal to 3 and so on. So what this m, what we have now the index for this field tell you is how many half cycle variation of the electric field amplitude, or for that matter magnetic field amplitudes, would be there in the direction transverse to the direction of the net wave propagation. So if m equal to 0, there is no variation, that is what this would mean. So m equal to 0 means the constant field, m equal to 1 means half cycle, m equal to 2 means 2 half cycles, m equal to 3 means 3 half cycles, and so on. So m equal to 0 means constant. So that means if I consider now a field for which m equal to 0, the field is constant in the transverse direction, it does not vary, and in this case the electric field is oriented like this. Now we know, since these are the conducting boundaries, the electric field must be 0 here, it must be 0 here, because this is a tangential component to the conducting boundary. So for m equal to 0, we do not want any variation of the field, and it should be 0 here and here. That can only happen if the field is identically 0 everywhere, and that is what precisely these expressions are telling you, that when you put m equal to 0, these fields cannot survive. So the lowest value of m which can survive, the field which can survive for that lowest value of m, they will be corresponding to m equal to 1. So that means the modes which can survive for transverse electric mode, the lowest mode which can propagate in this structure is the TE 1 mode. This is the lowest mode. So, for a given spacing of this conducting planes, we must have this value m which is at least 1, then and then only the fields will exist inside the structure. If m equal to 0, then the field will not exist inside the structure and the wave will not propagate. So, depending upon the size, as we saw, there will be finite number of modes. So, you can have first mode to propagate, which is T1. If the size is sufficient, you may get T2, you may get T3 and so on. So, on a given structure, you can have multiple modes propagating depending upon how many angles can be satisfied for this m. But for the lowest mode, when m equal to 1, one can ask, what is the wave which can survive in this? That means d, this is the largest value we can have, which is equal to 1 for theta equal to 90 degrees. So, if I take this is 1, then lambda by 2 will be equal to d. So, the separation between the plane is lambda by 2 for propagation of this T1 mode. It should be at least lambda by 2. If the separation is less than lambda by 2, I cannot have an angle d is less than lambda by 2 for m equal to 1, this quantity will be greater than 1. I do not have a physical angle at which the wave can be launched. So, what that means is, for this lowest mode to propagate inside the structure, my d should be greater than or equal to lambda by 2. And that is a very important conclusion. What that means is, once the separation between these two planes is given, that means the height of the parallel plane waveguide is given, I require a wavelength which is small enough so that this condition is satisfied. Or if I invert this, essentially I get my lambda should be less than or equal to 2d. So, only those wavelengths, since this has to be less than this, that means the frequency has to be above certain value so that this condition is satisfied, then and then only the wave propagation will take place. If lambda is greater than 2d or frequency is less than certain value, then the wave propagation cannot take place inside the structure. So, from here we get a important concept of what is called cutoff of a mode, that is, when this condition is satisfied, d is equal to lambda by 2, that frequency or lambda is equal to 2d for the equality condition, that is the lowest frequency which can propagate on a waveguide whose separation is d. So, from here essentially we can get that lambda maximum, this is the largest lambda which can propagate on this, that should be equal to 2d. Or if I write in terms of the velocity and the frequency, this is velocity of the wave in that medium, let us say denoted by c, divided by the minimum frequency which can propagate on this, that is equal to 2d. So, from here I get f minimum is equal to c divided by 2d. Below this frequency the wave does not propagate, and that is the reason this minimum frequency for this mode, for m equal to 1 mode, we will call as the cutoff frequency of that mode. So, for a particular mode to propagate, the frequency must be above that value, and that value is what is called the cutoff frequency of that mode. So, we have a concept what is called cutoff frequency and that is the lowest frequency which will propagate inside the structure for a given mode number, given m. So, as we can see, as the mode number increases, when it becomes T2, then the frequency will be doubled and so on. So, that is the reason we are saying this is the lowest mode, because that is the lowest frequency which can propagate in this structure, and that will be in the mode which will be T1 mode. Now, if I put this condition that this quantity your d equal to lambda by 2, if I put in our propagation constant expression, this is the phase constant which I had for these fields, and if I put m equal to 1 and lambda upon 2, this quantity here is equal to d, then m lambda upon 2d, that will be equal to 1. So, this quantity beta bar essentially will go to 0. So, at this frequency, when this condition is satisfied, what we call as the cutoff frequency, at cutoff frequency the phase constant of this wave goes to 0, and below this frequency this quantity is greater than 1. So, this quantity is imaginary. So, beta becomes imaginary, that means it is no more a phase constant, but it becomes attenuation constant, and the wave loses the wave nature. It represents only the field which exponentially dying down, because we have only attenuation constant and there is no phase constant. So, when you have a frequency below this cutoff frequencies, it represents the field which are exponentially decaying fields, but there is no propagation of electromagnetic wave. So, what we see from this analysis is that when we have a bound structure like a parallel plane waveguide, firstly there are discrete angles at which the uniform plane waves can be launched inside this. Superposition of this uniform plane waves which are bouncing back and forth between two parallel planes gives you the field distribution which will be like this, and those field patterns we call as the modal patterns. And we also see that for a given mode number, or to have a particular mode pattern excited inside the structure, the frequency has to be above certain value, what we call as the cutoff frequency. So, depending upon which order of the mode you want to excite, you require a minimum frequency, then and then only that particular mode will get excited. So, even if the waveguide is capable of supporting different values of m, it will depend upon the frequency whether that value of m will be acceptable or not, because whether this condition, that frequency is greater than cutoff frequency, is satisfied or not. So, this is now a basic picture of modal propagation in a bound structure like a waveguide. So, we will elaborate on this, and then following this essentially we will try to see another mode when we meet in next lecture, and then we will go to the more complex structures like the rectangular waveguides.